Hi, welcome everyone. Welcome to today's presentation on inside the large language modules. If you have ever wondered what actually happens behind the scenes when you type a prompt into a ChatGPT or a Gemini or Claude in your right place, today we are breaking down the complex mathematics and computer science behind the modern AI into clear institutive concepts covering everything from tokenization and vector embeddings to the grounding transformer architecture and self attentions. Okay, so major LLM platforms overview. Let's kick things off by looking at the current LLM landscape. Broadly speaking, the AI world is divided into two major ecosystems. First, we have commercially proprietary APIs like OpenAI, ChatGPT 4.0, and Anthropic's Cloud 3.5 Sonnet, and Google's Gemini. These are hosted in massive cloud data centers and and offering a cutting edge performance and zero maintenance, but operating as closed black boxes. Second, we have the booming open weight ecosystems led by models like Meta's LLAMA 3.3 and DeepSeek. These allows developers to download models weights directly, host them locally on private servers, and fine-tune them for complete data privacy and custom controls. Okay, then now transform architecture core. Now, why did AI suddenly explode after 2017? It all comes down to the transformer architecture. Introduction in the famous research paper, attention is all you need. Before transformers, older models like RNNs processed text sequentially, one word at a time, like reading a book through a tiny keyhole. It was slow and struggled with long sentences. So the transformers changed everything by processing all words in a sentence simultaneously in parallel using GPU hardware, unlocking massive scalability. Then now the token and vectors embeddings. So how does a computer actually read human language? It doesn't read words, it reads numbers. First, raw text undergoes subword tokenizations, breaking words down into smaller chunks called tokens. For example, a common word might be one token, while complex words get split up. As a rule of thumb, 100 English words equals about 130 tokens. Next, these tokens IDs are mapped into high dimensional space as vector embeddings. Imagine a 4000 dimensional coordinate map where words with similar meanings like king and queen or cat or dog are placed right next to each other. Okay, next fifth slide gonna like self attention mechanism. The absolute heart of the transformer is a self-attention mechanism. This allows tokens to communicate with each other to figure out context. For instance, in the sentence, the bank of the river, how does the model know the bank isn't a financial institutions? It computes 3 internal vectors for every token. A query, what am I looking for? A key, what features do I contain, and a value, that what information do I carry. By taking the dot product of query and key vectors and scaling them with softmax, the model mathematically calculates how much weight bank should place on the river. Okay, next slide says multi-head attention and positional encoding. To make this even smarter, models use multi-head attentions. Instead of calculating attention just once, the model splits into multiple heads running in parallel. One head might focus on grammatical relationships, another are on pronouns, and another and another overall sentiment. And since transformer process all words at once, they need a way to know word order. That's where positional encoding comes in. adding unique mathematical signature to each embedding, so the model knows the difference between a dog bites a man and a man bites a dog. So next slide gonna be context window boundaries. Every language models operates within their context windows, which is the total amount of text, both your prompt and it generated response, that the model can hold in its active memory at one time. Modern models have expanded from 4,000 tokens all the way up to 1 million tokens or more. But here's the catch: as context grows, the computational cost increases quadratically. If your conversation exceeds the window limit, the model starts dropping older tokens, which causes memory loss or topic drifts. Okay, next, effective prompt engineering. Knowing how LLMs process information helps write a better prompt. Three key techniques to get the best performance are: role definition. Give the model a clear person constraints and a target format. For example, act as a senior software engineer. So, few short learning, show, don't just tell, and give 2 or 3 examples of input and desired outputs directly inside your prompt. Okay, chain of thoughts prompting, like instructing the model to think step by step, forces it to generate intermediate reasoning tokens, drastically reducing logic and max mistakes. So next slide gonna be multimodal AI and ethics. As AI evolves, we are moving from text-only model to multimodal AI. So where text, images, audios, and code are mapped into the same unified vector space. However, we just remain aware of key limitations like hallucinations, where the model confidently generates plausible sounding falsehoods. And from an academic integrity standpoint, LLMs should be treated as powerful learning tools and brainstorming patterns. Brainstorming partners, never as a replacement for critical thinking. So the key takeaways and conclusion to wrap it all up: large language modules are fundamental statistical pattern recognizers. They convert text into numerical tokens, map them into high-dimensional vector spaces, calculate attention weights to capture context, and predict the most likely next tokens. Thank you so much for listening, and I would love to open up the floor to any questions. Your interactive HTML presentations deck is ready. Let me know if you would like any design tweaks, layout, assessments. Thank you.